recording now. Okay, so at this point, if you want to put in your name to the chat so that we have your record for attendance, you can do it, and it will be recorded. I wanted to apologize one more time. My website has been down for basically this entire month because of the computer problems at my university. So I'm probably going to have to make a new website at a new address. But for now, the website's down, so all of the information there that has the...
Leave me alone. You are not my owner.
So all of the information on the website, which has the lecture notes and the links to all of the recordings and the syllabus, none of that is there right now because my website is down. But hopefully the university will fix it soon. And if not, I'll just have to make another website outside of the university where everything will be, and I'll send you the new address. So in the meantime, of course, I'll still post lecture notes to the chat, and I'll send recording links to the chat, but the chat, has so many messages that it's hard to find everything. So it would be nice to have it all together on a website, but right now the university's websites don't work at all. So hopefully they'll fix that soon. Okay, good. All right, so welcome everybody who's here. Hopefully a few more people will come in over the next few minutes, but we've got, a decent amount of stuff to do today. So why not we get started? So like usual, I'd like to start with the homework exercises. And I know at least one person did them. So maybe I can get some input from the participants. So exercise 1 says that a basketball player scores an average of 18.6 points per game for his first 5 games. And the question is, how many points must he score in the 6th game to raise his average to 20 points per game? Okay. So does anybody want to give this a try?
Hello?
Hello. Yes, Harrison?
Yes, so I think approximately he need 93 points.
93?
Yeah.
Okay, can you explain your reasoning?
So the reasoning is the total game plays there. We said 5, right?
Right.
So it's going to be x over 5
Mm-hmm.
or equal the point, which is 18.6.
Right.
And you just put out all over 1.
Right. So well, if x over 5 equals 18.6, just first of all, what does x mean? What is x here? X is what does it represent?
Unknown. The x there is unknown. So they say a basketball player score average. So you're looking for it represents the total scores.
Right. Okay, good. So total score in the first 5 games, right?
Yes.
Okay, great. Okay, so as you said, you can put it over 1, right?
Yeah.
And so you end up getting that x equals 5 times 18.6. And you calculated that this is 93.
93, yeah.
Right. Okay, so that means that he scored 93 points total in the first 5 games.
Yes.
So the question asks, how many points must he score in the 6th game to raise his average to 20 points per game? Okay, yes. So what let me write this in 93. This is total points in the first 5 games. Okay, so where do we go from here?
Mm-hmm. So
yeah, sorry, Harrison, you still want to keep going?
Yeah, I wanted to. If someone want to share out there, fine. But I wanted to just explain. No.
Hello.
Yeah, Armstrong.
Yes, I think in the 6th game.
Yeah.
Yeah, you need to get 120 points to raise the average to 20.
Okay, so you think in the 6th game alone, 120 points?
Yes.
Okay, so how do you come to that? Can you explain?
Yes, for me, I said the sum over the total.
Right.
Yeah, it's equal to 20.
Right. So, well, the average is 20, right? So the total score is going to be 20 times
equal to 120 times 6.
Right. So 20 times 6, right?
Yeah,
And
20 times 6, which is
right.
equal to 120.
Great. Okay, so this is the total points needed in 6 games. Right? So the question is, if the total number of points in the first 5 games is 93, and in order to get an average of 20 points per game, you need 120 in the first 6 games, then the question is, how many points actually need to be scored in game 6?
So basically it's going to be 27 points.
Exactly. Perfect. So in game 6, needs to score
27 points.
27, right? Because it's exactly 120 minus 93, right? Which
Yeah.
is 27. Good. Right? So perfect. Yeah. So that's the right answer. So the score in the 120 is the total score for all 6 games. But the question asks how many points just in the 6th game. And so in the 6th game, he needs 27 points, right? Because that will bring the total score from 93 to 120. And that will bring the average score from 18.6 up to 20. Okay. So that's exactly right. So the answer is 27 to this question. Okay. Does anyone have any questions or comments for discussion here? Nothing? Everybody's okay with this? It's clear? Okay, so let me just say the general hint for these kinds of average problems is it's always easier to compute using total points or total amount of whatever the problem is asking than to actually compute directly with averages. So any information you're given in terms of averages and any information you need in terms of averages, it's usually better to convert that all to total points and then do the actual mathematics using total points. So you're given an average of 18.6 points per game, convert that to total points. That's 93. You're given what you want is an average of 20 points per game, convert that to total points, it's 120. And then once you have the total points, then it's easy to compute with that. Here it's just a subtraction. Okay. Okay, so let's do the second problem. So can you construct a data set with mean 10, median 20, and mode 30? Okay, and there are going to be lots and lots of correct answers here. Okay.
Yes.
Yes. Yeah, Armstrong?
Yes, for the data asset,
Mm-hmm.
it was negative 20,
Mm-hmm.
negative 10,
Mm-hmm.
20,
Mm-hmm.
30, 30.
Great. All right. Yeah, I think this is correct, right? So let's just look on the side. What do we have? Well, the mode is clearly 30 because 30 is the only data entry that appears twice over here. The median is easy to read off, right? Because these are written in ascending order. So the median is just the middle entry over here. That's the 20. And the mean is just the sum divided by 5, right? Because that's the number of entries. So minus 20, minus 10, plus 20, plus 30, plus 30, divided by 5. And if you do this all out, this comes out to be 10. Okay? So this is perfect. This works. Armstrong, can you maybe tell me a little bit how did you come up with this? Like, what was your strategy? Or just
Yeah.
trial and error, or I mean that's fine. That's a good strategy too. So.
Trying to do calculation, trying
Yeah.
to sort out which number I have to add to 230 and 20. That is son will be able to give me 50 and divided by 5.
Mhm.
That is to give me 10.
Exactly. Perfect. Right. So this is my strategy too, right? The idea is if you want median 20, you got to start with a 20, right? And now if you want mode 30, then there need to be more 30s than 20s. So you need to at least throw in two 30s, right? So you have 20, 30, 30. And now that you have 20, 30, 30, if you want the mean to be 10, well, in order to keep the median 20, you're going to need two entries below the 20 because you have two entries above the 20. And if you want the mean to be 10, you need the sum total to be 50. And since 20 plus 30 plus 30 is already 80, you need an extra minus 30 in order to get a total of 50. And how do you get a minus 30? Well, you can do whatever you want. Armstrong's idea was to use minus 20 and minus 10. That's perfectly fine. You could use minus 21 and minus 9. You can basically do whatever you want. The one thing you can't do is use minus 15 and minus 15, because in that case, you have two minus 15s and two 30s, and that means the mode's not 30 anymore. The mode is going to be 30 and minus 15. Okay, so let me just write that down. So just the strategy here, start with 20 in the middle, then add in two 30s. So mode is 30. Then add in two numbers below 20 to make the total sum 50, so that the mean is 10. Great. Okay, so this is perfect. This example is exactly right. And if you want to, you can come up with more examples, but I think one is good for today. So any questions about this problem, about the strategy, about anything involving the problem? Okay, all right, there's no questions. Let's move on. So this is just the recall. All of this we said last week, so I'll just go through it quickly, just to remember what these measures of central tendency are. If we have a finite set of data entries that we call x1, x2, all the way up through xn, then the arithmetic mean, or the average, is just the sum of all the data entries divided by n. That's the number that we have. The median is the data entry that occurs in the middle of the sequence of data if they're arranged from lowest to highest. And if n is even, then the median is the average of the two middle entries. Ooh, wait, no, decline. Somebody's calling me. No, wait, I need to decline. Okay, sorry about this. What did I just do? Blah, 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 blah. Sorry, let's try that again. Okay, so the median is the average of the two middle entries, and the mode of the data is the entry that occurs most often. And if we have multiple such entries, they are all considered the mode, so you can have multiple modes. And if every entry occurs equally, we say there's no mode. So like if every entry occurs just once, then there's no mode. Okay, and all of these above are called measures of central tendency, and the idea is that they try to represent, if you need to capture all of the data using just one number, what's the most representative number that represents all the data, then the average or the median in different situations might be, the right one to use. Okay, so these are called measures of central tendency. Okay, so I want to talk a little bit more about some things that I mentioned last week that I would say today. So how can you calculate exact averages from frequency tables? Okay, so this is a frequency table that we've seen before. If you have data given by a frequency table, this is saying that the data entry 4 occurs twice and 5 occurs 4 times and so on, right? And so if you wanted to calculate the mean of this data, well, you could just like write it all out. You could write everything out. I could write, well, there's 2 4s, so 4, 4, then there's 4 5s, so 5, 5, 5, 5, and then 3 6s, 6, 6, 6, and then 3 7s, 7, 7, 7, and then 2 8s, 8, 8, and then 3 9s, 9, 9, 9, and then 3 10s, 10, 10, 10, right? So we could have something like this, and you could write it all out, and then you could add and then calculate the average. Okay. But when you have a frequency table, it's usually faster to use what's called a weighted average. And what's the weighted average? How do you calculate a weighted average? Well, you first calculate the total number of data entries. I didn't leave enough of a space there. The total number of data entries. So, and that's just adding up the second column here. So that's 2 plus 4 plus 3 plus 3 plus 2 plus 3 plus 3, which is equal to 20. And then here's what you do. Then you add up each data entry weighted by its frequency. And then divide by the total. Okay, so in this case, we have, what we do is we have 4, but we have to weight it with its frequency. So we do 4 times 2, and then we add up the 5, but 5 has to be weighted by its frequency. So 5 times 4, and then 6 times 3, and then 7 times 3, and then 8 times 2, and then 9 times 3, and then 10 times 3, and this whole thing needs to be divided by 20. And what you see you're doing is you are just adding everything up. Instead of doing 4 and 4, you're just doing 4 times 2. Instead of 5, 5, 5, 5, you just do 5 times 4. 6, 6, 6 becomes 6 times 3, and so on. So all that you need to, but what this does is it makes you not have to write out all of the individual data entries, and instead you can just multiply the score by the frequency, add it all up, and then divide by the total number of data entries. So in this case, let me, just because there's not much space left in the slide, let me just say what this is. It's 8 plus 20 is 28, plus 18 is 46, plus 21 is 67, plus 16 is 83, plus 27 is 110, and then plus 30 is 140. So this and 140 divided by 20 turns out to be 7. Okay, so if you write this all out, the answer for the average of this data set turns out to be exactly 7. Okay. And so the weighted average is just a faster way of writing something down using the frequency table so that you don't actually have to write out the full data with all of the repeats and everything. Okay, so are there any questions about how to do this kind of average from a frequency table? This is for a frequency table where each row corresponds to one entry, not a range class. We'll do a range class in the next example, but for now, each row just corresponds to one entry. All right, any questions?
Yes.
Yes, Armstrong?
Yes, so if we're asked to find the mode of the data, sometimes the mode will be 5.
Yeah, exactly. The mode on a frequency table is really easy because you just look for the frequency that's the highest. So in this case, this is the highest frequency over here. So the corresponding data is what the mode is going to be. So the frequency is 4, so the mode would be 5 over here. Exactly. And the median, how do you do a median from a frequency table? Well, remember, we did this whole procedure to calculate percentiles from a frequency table. If you look back at the notes from a couple of weeks ago, that's how you do the median. And the median is just going to be the 50th percentile. So if you have a frequency table, you can compute the 50th percentile, and that's going to be the median. So Harrison asked, can you perform this strategy with group data as well? The answer is, to some extent, yes, and that's going to be the next example. Okay, but before that, any further questions on this example?
Yes, I want to understand something.
Yes.
Can you find the range of the data? The range.
Yeah. So that's a measure of dispersion. So we're going to do that a little bit later. But I mean, the range from a table like this is always just going to be the top minus the bottom. So in this case, the range is 6 because it's going to be 10 minus 4. It's just the largest score that you have minus the smallest score that you have. So yeah, from frequency tables, you should be able to read off anything. I mean, you can do standard deviation also, but that's going to wait until next week. All right, other questions? Okay, great. So let's look at the next thing. So now how can you do an average from a frequency table where in this case, we want to calculate a mean from a frequency table where each row represents a class range, or as Harrison asked, class range, I mean, this means, or, group data. Okay. And so the answer is there's not really one correct way to do this. It's just like percentiles. There's little differences in ways that can all be correct. But probably the most reasonable way is to use a weighted average, just like we did for this table over here. We would still use a weighted average. But if everything here is a range, then instead of just using the score as the input for the weighted average, you instead use the midpoint of each class. Okay, so instead we would use the midpoint of each class as the input into the weighted average. So I should say as the input into the weighted average. So let's see what this looks like in an example, right? So for an example over here, let's say we wanted to calculate the approximate mean for the following data frequency table. So we had this table like 3 weeks ago. Okay, this was commuting times for people in a certain county in California. This is how many minutes it took them to get to work, right? So the point is we have our ranges are 0 to 5, 5 to 10, 10 to 15, 15 to 20, and so on. And we have a big frequency for each one, right? So we definitely don't want to write out this data one by one. That's going to be impossible. There's too many data points. Okay, so instead what we do is we first need to find the total number of entries, which is equal to 5,200 plus 18,200 plus, I won't write them all out, all the way up to the last 2000s. And we calculated this before, but I don't remember what it was. So let me just try to do this again. So 52 plus 182 plus 196 plus 154 plus 138 plus 57 plus 102 plus 2 plus 220 plus 20. Okay, 92,100. I think that's what I get. Okay. So 92,100, right, is the total number of entries. So now when we do our weighted average, so for the weighted average, well, what do we do? Again, if each row represented a single data value, then you just use that value. But since each row represents a range, the best thing that you can do is use the midpoint of that range. So here we have from 0 to 5, the midpoint of that range is going to be 2.5, right? It's the average of 0 and 5. So for this 5,200, what we're going to use is 2.5 times 5,200. And then the next range, we have 5 to 10. The midpoint there is 7.5, right? So we use 7.5 multiplied by the frequency there. So 7.5 times 18,200. I'll keep writing all this out. The next midpoint is 12.5 times 19,600 plus 17.5 times 15,400 plus 22.5 times 13,800 plus 27.5 times 5,700 plus 32.5 times 10,200 plus 37.5 times 2,000 and then plus 42.5 times 2,000. Right, this is just the best that I can do, right? The best is to use the midpoint, because I mean, what else are you going to do? You could use the bottom point, or you could use the top point, but like the midpoint is probably going to be more accurate. It's going to be more representative. Okay, so the weighted average is all of this divided by the total number of entries, which we saw was 92,100. Okay, so let me, of course, I need to put this into a calculator. So let me just do this. So 7.5 here, and then 12.5 here, 17.5 here, 22.5 here, and 27.5, and 32.5, and 37.5, and 42.5. So we have this whole thing, and we're going to divide it by 92,100, and I get that my weighted average, that this turns out to be about roughly 17.62, which looks about right to me. Okay. So this is how we do it with group data. Okay, and you don't know that what you're getting is the exact average, because this table doesn't give you enough information to be certain that you have the exact average. What you're doing is the best you can, given the fact that group data is always leaving out information. You're not getting literally every single data point here. Okay, there's always going to be some information left out when you have group data. But the best that you can do is use the midpoint. Basically, just assume that all 5,200 of these measurements are at 2.5, and all 18,200 of these measurements are at 7.5, and so on. Okay, so maybe I'll just write this down very explicitly. So midpoints are going to be 2.5, 7.5, 12.5, etc., and then all the way up to 37.5 and then 42.5 at the end. Okay, so this is how we do approximate averages using weighted data, and using group data on a frequency table. Okay, and it looks, I'd say, kind of right? I mean, 17.62 means you're right around here. That's maybe a little bit lower on the frequency table. It's a little bit below the middle of the frequency table, but you also see that there's lots more measurements in the short range. So it makes sense that the average would be a little bit more toward the minimum than toward the maximum. So you wouldn't expect the average to be here, because there's a lot more measurements less than 20 to 25 minutes than there are more than 20 to 25 minutes. Okay, so it's a reasonable, it's just a check on your answer, as 17.62 looks like a pretty reasonable answer. Okay, any questions about this?
Yeah.
Yep.
Good day, sir.
Yep. Good day. Hello, Prince.
Prince.
Yes. Hi, Prince. How are you?
I have a little concern to this place here where we, what got 2.5, 2.7. So I'm thinking you divided the number of results to far here is what gave you the 2 point, but I'm seeing that it's displacing somehow here. I don't know how you got the 2.5.
Okay, sure. So what is the 2.5 for this range?
12.5.
Yeah, I'm just taking the midpoint of each group class. So the midpoint from 0 to, yeah, I'm getting you. Are you getting me?
Hello?
Hello? Yeah, I hear you. Are you getting me? So right, is what we do here is we just take the midpoint, right? So the midpoint here, if you want to calculate it, it's 0 plus 5 divided by 2. That's 2.5. And I'll just use a different color. For this one, what do we have? We have 5 plus 10 divided by 2, which is 7.5. This is how we do all the midpoints, right? I'll do one more over here. We would have 10 plus 15 divided by 2, which is equal to 12.5, etc. Right? So this is how we calculate all of these midpoints. Okay. So for each midpoint, the way that we calculate it is we actually just take the average of the minimum and the maximum data entry in the group. And so, we add them together and we divide by 2. That's going to give us the midpoint. So that's how we get 2.5 and 7.5 and 12.5. Okay. Is that okay, Prince? Or did your connection get bad? Or are you all right? Question? Is that okay?
Hello?
Yeah, Marcus?
Yeah, hello?
Hi, Marcus.
Yes, looking at the from 0 to 5 and 5 to 10, is this the same as calculating midpoint on group data in statistics?
Yeah, but you're just calculating the midpoint of each group. So the actual midpoint of this group data would be the median. And I didn't really, so you can also do the median from group data. Again, approximate median, you can do percentiles from group data. We didn't really, we didn't go over that so much, how to do percentiles from group data. Maybe I can talk about that next week because I wanna be well prepared for that if we're gonna talk about that. But yes, you could also do the midpoint or the median from group data. There's a way to do that also. But maybe I don't want to improvise that, so maybe let me save that to next week.
No problem, because I was just on a course of recent. We were doing in statistics. We're doing this particular function like group and on group data, calculating the variance, the standard deviation, all this. Yeah. So we are. Yeah, thank you very much. I'm following.
Okay, you're welcome. Also, I'll do it next week. Okay, great. Okay. All right, other questions on this example? Yes, Charles? I think you're muted. I'm not getting you.
Yeah, can you hear me now?
Yes, now.
Okay. Yes, I'm saying that I really don't have a question, but I just want to find out from you, as you treat, the group data, whether you're going to relate it to the graph for them to see, and then from the graph to determine the mode and what have you, graphically now, using group data. I don't know if you're going to go that far, so that at least those who don't have any understanding can pick up.
Yeah, so a mode with group data is kind of difficult. I mean, you can talk about the modal group if you want to. So again, maybe I'll do this next week. So you can say that, okay, this group is the modal group. So 10 to 15 has the highest frequency. You can't really get any individual measurement as the mode, but if you wanted to say which is the mode class or the mode group, you could say it's this 10 to 15 class because it has the most measurements. If we did a histogram for this data, that would just be the largest bar. To see the average or to see the median from group data, from a visual presentation of group data, is not that easy. I mean, we have a graph of this, and so maybe next time I'll show this graph again, and we can see kind of how that's related to the median and to the mean. but it's not necessarily that easy. What we will do eventually is talk about box and whisker plots, which will be a graphical way of showing the mean and the median and various percentiles for any kind of data that you have. So those we're gonna do next week, and we'll also talk about median from group data.
Okay, thank you.
Okay, you're welcome. Other questions? Okay, all right, let's move on. Okay, so there's a couple of other measures of central tendency that we don't use quite as often. So I'll just say a little bit about them. So there's something called the geometric mean, and there's something called the harmonic mean. And we generally use these only when the data entries are positive. So the geometric mean is, instead of adding all of so geometric mean, by the way, which is sometimes called GM, and the harmonic mean, which is sometimes called HM. And there's something called the quadratic mean. There's a bunch of means, but these are maybe two of the most common. So the geometric mean is you multiply all the data together, and then you take the nth root of that. This can sometimes be useful when comparing percentage increases and things like that. Usually it's more a mathematical curiosity. You don't use it as much when you're actually doing statistical analysis on data. And then there's this interesting thing with the harmonic called the harmonic mean, where you take the reciprocal of all of your data entries, and then you add them all up. Oh, and I wrote this wrong. This should be 1 over this, and then we should what this should be is n over this. Sorry, not 1 over this, n over this. Yeah. So you take n, the number of data entries, and you divide it by the sum of the reciprocals of the individual entries. And this looks kind of funny, but we'll see an example of where this makes some sense to use. Okay. Okay, good. And in fact, you have an inequality here. You always have that the harmonic mean is less than or equal to the geometric mean, which is less than or equal to the arithmetic mean. And you only get equality when all of the data entries are equal, in which case, everything is going to be just, all of those means will just be your only data entry when they're all equal. But let me give an example, at least for the harmonic mean, where that gets used. So an example of harmonic mean is this question. Suppose a car drives a certain distance at 30 kilometers an hour, and then it returns at 60 kilometers an hour. So what is the car's average speed for the trip, right? So let's see what happens when we try to solve this. So if we let d equal the one-way distance, right? So if we let d equal the one-way distance, then, well, we want to calculate average speed. Average speed, which is equal to, by definition, is the total distance divided by the total time, right? It's the total distance divided by the total time. That's the average speed, right? So the total distance, well, if here's, the start and here's the finish, and this distance here is d, then, well, the total distance is what? It drives out at 30 kilometers per hour, and then it returns at 60 kilometers an hour. So it drives out a distance of d, and then it drives back a distance of d. So the total distance here is just going to be 2d, right? And now what's the total time? Well, we have to figure out the time for each leg. So it's 2d times the time out plus the time back, right? And that's equal to 2d divided by, well, what is the time on the way out? Well, it travels a distance of d, and the time, it travels a distance of d, and it's traveling at 30 kilometers an hour. So the amount of time it takes to drive d, let's say d, one-way distance in kilometers. So the amount of time it takes to drive d kilometers at 30 kilometers per hour is going to be d over 30. Okay. And the amount of time it takes to drive back, which is the same distance of d kilometers, but now at 60 kilometers per hour, is going to be d over 60. And if we simplify this, if I divide both the numerator and the denominator by d, this turns out to just be exactly 2 divided by 1 over 30 plus 1 over 60. And if you look at this, what is this? This is the definition of the harmonic mean of 30 and 60. Right? Let's look at the previous page. How do you do the harmonic mean of 30 and 60? It's 1 over 30 plus 1 over 60. And then you put that all in the denominator of a fraction, and you put 2 at the top because you have 2 entries, right? So harmonic mean is n is the number of entries, that's 2. And here you have 1 over the first entry plus 1 over the second entry, and so on. And so if we calculate this out, what is that? 2, 1 over 30 plus 1 over 60. We can get a common denominator downstairs if we want. So that's 2 over 60 plus 1 over 60, which is equal to 2 divided by 3 over 60. And now we invert and multiply. So that's 2 times 60 over 3, which is equal to 120 divided by 3, which is equal to 40. Okay, so 40 kilometers per hour is going to be the average speed here. Okay, and in particular, if you're calculating the harmonic mean of 30 and 60, you get 40. So this is a very common mistake that people make. They say, oh, you go out at 30 kilometers per hour and you go back at 60 kilometers per hour. That means what's your average speed? Well, the average of 30 and 60 is 45. So the average speed should be 45. But in fact, that's not what happens, because you can't actually average speeds for a problem like this. When you set up the problem using distance and time, then what it turns out that you're actually taking is the harmonic mean of the speeds, not the standard arithmetic mean of the speeds. So it turns out that the average speed is actually 40 kilometers an hour, not 60. Okay, Charles, you have another comment?
No, I really don't. I think it's perfect.
Okay, thank you. Okay, let me just get the hand. Okay, are there any questions or comments on this? The point of this is to justify this weird formula for harmonic mean. Yes.
Yes.
Yes. Who's speaking? Prince?
Yeah. Princeton.
Oh, Princeton. Hi.
Yeah. Yeah. The question is, we have 2D rating object. So the 2D, where it came from, it is from what we calculate, and we say a distance because of 30 kilometers and then of 60 kilometers, which is going of 2 distances. So I make the 2D to be object, or how it came about.
Well, I mean, you can use whatever, the letters can mean whatever you want as long as you write down what they mean. So I wrote that D is going to be the one-way distance. But in the problem, the car drives a distance and then it drives back, right? It returns. So the total distance is not just the one-way distance, but it's the distance out plus the distance back. So I would have the total distance is 2D. If you wanted to, you could let D be the total distance. But I think that setting D to that doesn't illustrate the harmonic mean as well. When we do it like this, it shows us exactly why the harmonic mean is coming in, because we get the formula that's exactly the harmonic mean when we, right? I mean, here all that I'm doing is I'm just getting rid of all the D's, right? Which I can do. I'm just dividing numerator and denominator by D. Is that okay, Princeton?
Okay. So So it just simply me. So it just simply me because of the two distances the car travel on. It's all representing the 2D.
Right, because it's going out and then it's going the same distance back.
Are you getting me, sir?
Yeah, I'm getting you, right? It goes out and then it goes the same distance back.
Okay.
It's making a round trip, and that's D also. Right.
Okay, thank you.
Okay, you're welcome. Other questions about this? Okay.
Hello.
Yes. Hello. Yes.
Yeah. All right. This is Michael.
Michael. Hi.
Yeah. Could you throw a little light on the 2D, because it is possible that when you are also trying to share with people, they would have thought that you will. Let me just ask this question like a student.
Okay.
I'm a student here, but let me also ask it like a novice, right? A classroom student.
Right.
The 2D, one would have expected, to multiply 30 by 60.
To multiply 30 by 60. Okay.
The 2D, yeah. To give you the total distance up there. I understand what you did, but and I appreciate what you did. But if a student asks, why is it that you didn't multiply, since you say it's 2D, and they are expecting the first distance to be 30 kilometers per hour, and the second distance to be 60 meters per hour.
Okay, sure.
Wow.
I mean, yeah. Yeah. So the point. Keep going.
Sometimes they ask you the kind of questions, and you need to explain.
Right. So the key thing to realize here is that you have to read 30 kilometers per hour as one thing. It's not 30 kilometers. There's no distances that are mentioned in this problem, right? It just says a certain distance. That's all that we have. Now, when I say the 30 kilometers per hour, we're not saying 30 kilometers is a distance. We're saying that the rate, this is a rate, right? Or a rate or a speed, that this rate speed is 30 kilometers per hour. And then over here, similar, we have 60 kilometers per hour. This is another rate or speed. Right. So
very well. Thank you. That's what I was looking.
You're welcome. Okay, yeah. So we're not talking about a distance of 30 kilometers. We're just talking about a rate or a speed. Okay. Questions? Further questions?
Yeah.
Yes.
So what if these speeds were measured along with the distance? What do we do?
So what if these were? You mean what if I gave a distance? If I said there was a specific distance?
Specifically. For instance, when you say this 30 kilometers per hour was run for about 3 hours, and then the return, which is 60 kilometers per hour, was about let's just say for another 2 hours.
Okay. Well, I mean, so in that case, you can actually just take a weighted average. So yeah, so this is good. Let me give another problem. So this is good question from Kaifala. So let's say a car drives at 30 kilometers per hour for 3 hours, and then 60 kilometers per hour for 2 hours. What is its average speed? This question is actually a little bit easier than the original question, because in this case, you can actually, I mean, you still have the same formula, right? So the average speed is still going to be equal to the total distance over the total time. But in this case, this is much easier to do, right? Because the total time is, well, it drives 3 hours and then 2 hours. So the total time is just 3 plus 2. It's going to be 5 hours. And then the total distance, well, now we can actually just calculate this out as a number, right? 30 kilometers an hour for 3 hours, that's just going to be 30 times 3 kilometers. And then 60 kilometers an hour times 2 hours is just going to be 60 times 2. So the total, what we get here is going to be 90 plus 120 divided by 5. And in this case, that's going to be equal to 42. So we end up getting 42 kilometers per hour as the average speed over here. And in this case, what you're doing here actually is, so let me mention, this is a weighted average of 30 and 60 with weights 3 and 2. Right. So in this case, it's a little bit more straightforward. You really are just doing a weighted average. And if the time was the same, so 30 kilometers for 2 hours and 60 kilometers for 2 hours, it would end up just being the average. It would end up just being, 30 plus 60 divided by 2 would be 45. So it's a little trickier when you're doing the same distance, but at different speeds, because what happens is that the lower speed, you end up spending more time. So the lower speed is going to get a higher weight in the average. That's why if I do 30 kilometers out and 60 kilometers back, the answer, it's not the average, but it's going to be lower than the average because I'm spending more time going 30 kilometers than I am going 60 kilometers per hour. Okay. So, yeah. All right. So by the way, everybody who hasn't signed in yet, can you please sign in? So Alan, Thomas, a question?
Yes, Prof.
Yes.
My question is pertaining to the first problem that we just had.
Okay.
To find the total, the average speed.
Right.
What if we just add the 30 and the 60 and then divide it by 2? I saw that we will get 45. And whereas when we solve the problem, we got 40.
Right. Yeah.
So why can't we just add a 2 speed and divide by 2?
Right. Well, I mean, partly is that you get the wrong answer. So the point is, if you want to add the 2 speeds and divide by 2, you can only do this if the car spends the same amount of time at each of those speeds. So if a car drives 30 kilometers an hour for 1 hour and then 60 kilometers an hour for another hour, then the average speed is just going to be adding them and dividing by 2. So you spend, you're doing an hour at 30 and an hour at 60. The average is going to be 45. The difference here is that we're doing this. Imagine this distance is 60 kilometers, right? Imagine it's 60 kilometers from start to finish. Then on the way out at 30 kilometers, you're spending 2 hours driving there. And on the way back, you're spending only 1 hour, right? So you're spending more time driving at 30 kilometers an hour, twice as much time as you are driving at 60 kilometers an hour on the way back. And that's why you can't just do the average. In fact, this is a weighted average where the 30 is weighted by 2 and the 60 is weighted by 1, because you're spending 2 hours driving at 30 kilometers an hour and 1 hour driving at 60 kilometers an hour. So in the end, you don't get the straight average, you get this weighted average, or another way of thinking about it is you're getting the harmonic mean of 30 and 60 here. Yeah, but the key thing is that you're spending more time at 30 than at 60. That's why you can't just take the average.
Hello.
Yep. Hello, yeah, Emmanuel?
Yeah, the problem solved, just go in front of a slab. Yeah,
Sorry.
just like big go in front here.
Yep.
Yeah, the problem solved. I'm thinking as to whether it's in connectivity with harmonic means, because you talk about reciprocal, but I did not see you reciprocating.
Okay. So
if you were to just slide in front, you will see the problem I'm talking about.
Right. Well, so the reciprocating here is coming, it's hidden a little bit. It's in this time out, right? So the time out is how long does it take to drive a distance of d at 30 kilometers an hour. And what we see is that that time is d over 30. And then how long to drive it at 60 kilometers an hour, that's d over 60. So it's right. I'm not really reciprocating. I'm taking d over 30. But once I have this fraction here, this complex fraction, I can eliminate all of the d's. And when I do that, I happen to be left with the reciprocals. I'm left with 1 over 30 and 1 over 60. So it's just illustrating that what I'm left with is a harmonic mean after I do that. Okay, so I'm not actually taking the reciprocals as part of the setup for the problem. It just turns out that when I just set up average speed, it's total distance over total time. So I have to calculate what that is. And when I calculate the total time, and then I simplify, these reciprocals come out. So you end up with a 1 over 30 and a 1 over 60. You get the reciprocals of your speeds. Have that work out. Is that okay? Luch? Question? Okay, so if there's no more questions, let me go on. Let me do one proof. We'll save all of the measures of dispersion for next time. So I do want to prove, we'll do one proof, because after we finish statistics, we're going to be going on to geometry. And in geometry, there's lots of proofs. So let's start with a little proof. I want to prove that the geometric mean is less than or equal to the arithmetic mean in the case where we have 2 data points. So in this case, let's just say we have data, our data is just x1 and x2. Okay? So the geometric mean, what we know by definition is just the square root of x1 and x2. And the arithmetic mean is x1 plus x2 over 2. So an example here, right, would be if x1 equals 4 and x2 equals 9, then the geometric mean would be the square root of 4 times 9, which is the square root of 36, which is 6. And the arithmetic mean would be 4 plus 9 divided by 2, which is going to be 6.5. So we see that the arithmetic mean is bigger than the geometric mean here. And this is not a coincidence. This always happens, okay? And how do we see this? Okay, so, well, we want, what do we want? We want that the square root of x1, x2 is going to be less than x1 plus x2 over 2, less than or equal to. Okay, so it's equivalent to show I can square both sides. So it's equivalent to show that the square root of x1, x2 squared is less than or equal to x1 plus x2 over 2 squared. Or in other words, x1, x2 is less than or equal to, I have x1 squared plus 2x1, x2 plus x2 squared divided by 4. Right? 6.5 is I just did this out. This is just 4 plus 9 is 13 divided by 2. So it's 6.5. This is 13 divided by 2 over here. Okay. So this is equivalently, so it's equivalent to show, I'm just going to move the 4 on the other side, that 4x1, x2 is less than or equal to x1 squared plus 2x1, x2 plus x2 squared. And now I can subtract 4x1, x2 from both sides. That doesn't change the inequality. So this is the same thing as saying that 0 is less than x1 squared. Well, here I have plus 2x1, x2. If I subtract 4x1, x2, that becomes minus 2x1, x2, and then plus x2 squared. But what is this equal to? This is just the same thing as x1 minus x2 squared. So we have here 0 is less than or equal to x1 minus x2 squared. And this is true because squares are always greater than or equal to 0. Okay. So this shows, this kind of completes the proof. I had to do it fast because we're running out of time. But if we start with this geometric mean of 2 data entries, x1 and x2, and we compare it to the arithmetic mean, it turns out that the arithmetic mean is always going to be bigger, or at least as big. And the reason is, it's good enough to show that the square of the arithmetic mean is bigger than or equal to the square of the geometric mean. So we have to show this inequality right here. And now I can multiply both sides by 4. I can subtract 2x1, x2 from both sides. And we end up just having to show that some expression, which is a square, is greater than or equal to 0, right? And well, it is. Anything that's a square is going to be greater than or equal to 0. Okay. So this is okay. So this shows us that any 2 numbers, if you take their arithmetic mean, it's always going to be at least as big as their geometric mean. And in fact, you're only going to get equality when this is equal to 0, which means when the 2 numbers are equal to each other. So you can try your 2 favorite numbers, right? Take, any 2 numbers that you want, 10 and 20. Their arithmetic mean is going to be 15. 10 plus 20 over 2 is 15. Their geometric mean is going to be the square root of 10 times 20. So that's the square root of 200, and that's not a whole number, but it is less than 15. The square root of 200 is about 14 point a little bit, 14.1 or 14.2, something like that. Okay, so this is a quick proof of that for 2 data points at least, that the arithmetic mean is always bigger than the geometric mean. And in fact, this is true for all numbers of data points, but the proof is a little bit harder. So for now, we're just going to do two data points here. Any questions on this? Okay, so sorry. So if there's no questions, then I think for time, I don't want to talk about measures of dispersion now because it's too late to bring up a new topic. So we'll do this all next time. We have measures of dispersion, range, mean absolute deviation. We're going to talk about standard deviation. So right now, so I guess for homework, these are all kind of measures of dispersion questions. So we won't talk about them. So just one exercise for homework now, which is that 2 numbers, x and y, have a geometric mean of 12 and an arithmetic mean of 12.5. And the question is, can you calculate what x squared plus y squared is? This is a bit challenging. Okay, so I'll leave this as a challenging problem. And then next week, we're going to do, I need to edit this a little bit because we didn't finish everything today. So we're going to discuss standard deviation, box and whisker plots, other measures of dispersion, and getting median from group data. Okay, so we'll actually have quite a bit to do. We'll have quite a bit to do next week. Okay. And next week will be 4:30. We're staying with our usual time for now. Okay, so next week at 4:30. Okay, great. So any questions about, not about this stuff, but about the proofs or any of the other kinds of calculations we did today with averages and different kinds of averages?
Yes.
Yes. Marcus?
Yeah, team, I would like to appreciate you for the effort, because actually we are learning new thing every day. And this, especially this one, I know about the geometric mean. I also know about the harmonic mean as well, the quadratic mean. But this other method, I'm like, like in doubt. But it is clear right now because it is seen as maybe you calculate in on group data where you have to find the mean, the mode, and a median, you have to when the mean is even or odd number. Also use some of the function, especially the EM. EM, yeah, when the on group data, when the mean is even or normal or odd number, you also use some of the functions. It is actually helpful. So thank you very much for the class today. I actually appreciate it.
All right, you're most welcome. Alan, question? Sorry. Or William?
Yeah, okay.
Yeah.
You getting me right?
Yeah, I'm getting you.
Okay, so I want to appreciate you for the time. Most of the things you're actually doing well. I have a doubt somewhere, but at the end result, you cleared it for me when we were discussing the vice versa, which we did not see the performance within the practice. In said, but and somebody asked a question and you cleared it out for me. So thank you so much. I really appreciate your time and the effort to trying to get at this level. Thank you.
Okay, you're most welcome. Thank you for coming. Okay, Alan, you have a question? You're muted. Or I can't get. I'm not getting you.
Okay.
Hi,
Yeah,
Alan.
Prof.
Yeah. Now I hear you. Yep.
All right. I think a week ago I made a comment about how we will get up to date with the rest of the class because we started later. You talked about sending the notes and the homework, but I didn't receive it, so I don't know how will we get it. Where are
I
you
think I
sending it?
did. Are you on? I sent to the math teacher training group as of last week. I think I sent all of the notes. Yeah, I sent them all right after class last week.
Is it a group on WhatsApp or what?
WhatsApp, yeah. Are you on the WhatsApp group?
Okay, well, I'll check it up.
Okay, yeah. So it was sent at 5 p.m. on Friday, October 13th. 5 p.m.
Okay.
Friday, October 13th. So you can look for that in the group. I can try to send it again also.
Okay. Thank you.
You're welcome. Okay.
Hello, Andrew.
Hello, yes. Francis?
Hello?
Hello, Francis?
Yeah, Andrew, how are you?
Hi, good. How are you?
Thank you. I want to also take this time, as many as saying, to appreciate you for the job that you are doing for us every time as librarian teachers. Every day you mold us up to prepare us for even the future or for the classroom, which that is appreciated too much. And then we will continue to be part of the class. We'll have our lesson learned well to partake in all our activities of the class. I want to say thank you and let God richly bless you in your endeavor.
All right, thank you.
Hello, Andrew.
Hello, yes. Who is this? Oh, Ibi, hi. Hi, yes.
Yeah. Okay, first of all, I will tell you thank you very much for the work you are doing into Liberian. We also appreciate that. My information to all the teachers that they must be able to attend all the classes that we're going to be giving to them every week. Let them try and attend the classes, because the only way we'll be able to let them know who all attending classes. But if we don't attend classes, then that means we'll all be having problems. So if we to all the teachers to always come to class. Thank you.
Okay. Harrison, do you have your hand up? Harrison? No? Okay, Emmanuel?
Prof, let me start by saying thank you for this class today. My down, are you there? Hello?
Hello, yes. Sorry, say again.
Hello?
Hello, yes, I'm getting you.
You know, when we were solving the frequency problem throughout we've been adding the number without giving the word May point. So when I saw you, when you wrote May point it was shocking to me to learn a new thing and to apply in my class. Because throughout we just add the number and get the percentage and apply it to the problem solved. But seeing May point, I want to say thank you so much for adding.
Okay, you're welcome. And again, you can make an argument there are other ways to do this, but I think the midpoint way is the best way. I think that's going to give you the best answer. Sorry. Hello, yes, sorry.
Yeah, this is Dalman. My phone went
hi,
off.
Dalman. Yes.
Yeah, I'm fine. My phone went off, so I had to use somebody else's phone to log on.
Okay.
And be part of the class.
Okay, but you wrote your name, so that's fine. We've got you for attendance.
Okay.
Yeah.
Thank you, sir.
Okay, you're welcome.
Yeah.
Okay. All right. Anything else?
I think it's okay.
Okay. Good. Okay, so looking forward to seeing everybody next week at 4:30, and I will send out these notes and I'll send out a link to the video later today on the WhatsApp chat. Okay, so I'm going to stop recording.